Hi, I'm Madeline James, and this is the 12th part of my world building guide for creating an Earth-like fantasy world. To start back at part 1, you can watch Land Masses and Plate Tectonics, which I will link in the description below. In the last part, we mapped our past orogenies and shallow seas and our major rock type distribution. That'll also be linked below if you haven't seen it yet. This part is a direct extension of that part, and we will be building off of those maps to place our ore deposits. Consider resources by technological era, and take a look at gemology and where we would find different gemstones. Like the last part, one of the main resources I am utilizing for this step is Mineralogy 2nd edition by Dexter Perkins of the University of North Dakota, and Archaeometallurgy Materials Science Aspects by Andreas Hauptmann. And I'm also pulling from a number of other sources detailed throughout this part, and they will be in the resources section of the blog post. And again, a huge shout out to geologist Nikolai Hersfeld of World Building Pasta and geographer Ross Bay Geo, as he is known on YouTube, for their feedback and advice on this project. As we have already discussed, valuable metals and minerals are found throughout the crust, but in order for them to be found with enough density to form an actual deposit, they must be concentrated. The major ore deposit types are hydrothermal, magmatic, and sedimentary, but when you really look at them, they mostly form in and around magma. There are two main types. The first type is magmatic deposits formed through partial melting of the crust into magma, followed by that magma rising through the crust and progressively cooling. This usually happens deep in the earth, normally too deep to be mined, but can later be exposed by erosion and uplifting of the crust. The other type is hydrothermal deposits that form from the hot fluids that move through rock, most commonly released by magma, such as when it moves into lower pressures, but also from solid rocks or infiltrates from surface waters. And 90% of these deposits are concentrated through hydrothermal action. This melting can occur with subduction, compression, or injection of hot magma. Some of the most important sedimentary deposits, with a few exceptions, are made from the sediments or residuals of hydrothermal and magmatic deposits. Now, we don't care about all ore deposits. We only care about those that are ending up or at or near enough to the surface to be accessible. We are going to discuss some major types of ore deposits and where they form, and where we are most likely to find them. Then we will go through all of our technological ages, consider what resources were important for the period, and where they would be able to mine these resources. We will create maps per technological age instead of mapping out each deposit type, as this will give us a much better understanding of what was actually accessible where and when. Major sources for this section are the Ore Deposits 101, 11-part video series by Andrew Jackson, and Mineralogy 2nd edition, Chapter 9, Ore Deposits and Economic Minerals by Dexter Perkins. Let's start with hydrothermal or magmatic ore deposits. The most common places for hydrothermal and magmatic ore deposits are mid-ocean ridges, back arc basins, and volcanic arcs. Subduction zones, oceanic continental convergence, are one of the main places for hydrothermal vents, but most continental collisions, so continental-continental convergence, begin as oceanic continental subduction zones. So this means that most orogenies from continental collisions see the rocks formed in subduction zones, which are rich in hydrothermal and magmatic ore deposits, which are pushed up during mountain building. An example of this is the TEMB, or T-E-M-B, Tethyan Eurasian Metallogenic Belt, which runs across the Alpine Himalayan mountains from southern Europe, modern-day Iran, through the Himalayas, and down into Indonesia. Places like this will be incredibly rich in metal ores. We already accounted for this in our rock distribution maps, where we see igneous rocks in our continental convergence orogenies. Now, hydrothermal deposits are typically classified by the depth they are formed, among other things, which directly correlates to the type of igneous rock intrusion they are associated with. If you recall, the felsic end has lower melting points than the ultramafic end. So from the deepest in the crust to the surface, these deposits form in these regions. The deep crust or mantle, which is 10 to 50 kilometers deep, mesothermal, which is 1 to 10 kilometers deep, epithermal, 0 to 1 kilometer deep, and various other surface deposits. With our earlier maps, we have already kind of given us a good idea of where the different kinds of igneous rocks will be found, which will greatly help us with placing our ore deposits. But quickly, an important note. In terms of the prevalence of different deposits as sources for different resources, this is hugely dependent on technological capabilities. I will be discussing the deposits as sources based on current technology levels, but we will be looking at what would have been accessible in different times in the technological eras section. Let's start with the deep crust or mantle originating deposits and work our way to the surface. I am not going to go into much depth on each specific deposit type. There will be a bit more details in the blog post for each of these, and I'm not covering every single type of deposit, just the main ones I have found in my research. So in ultramafic deposits, I have kimberlites. Kimberlite is an ultramafic igneous rock found in the upper mantle, which can be pushed to the surface by volcanic eruptions in vertical shafts. On their way through the crust, they can pick up minerals of the lower crust, most importantly being just about the only way really good quality diamonds get to the surface. There are technically a few others, such as impact craters and lamprites, but they're almost always not as high quality or prevalent. But kimberlites are found almost exclusively within Archean cratons in clusters. So now for ultramafic deposits, we have mafic layered complexes, which are formed by layers of mafic and ultramafic rock, and occasionally felsic. And these are formed relatively deep in the crust. These deposits can have layers of mafic intrusions as copper-nickel massive sulfide deposits and platinum-chrome deposits. Next, we have three types of intermediate felsic intrusion. There are porphyries or porphyry-type deposits, which are hydrothermal deposits that form in and around felsic to intermediate volcanic magma chambers and/or cooling plutons. There are porphyry skarn deposits, which are relatively small hydrothermal deposits that also originate from porphyry magmas. And then last, there is iron oxide copper gold, or IOCG deposits, which mainly occur at major crustal faults, so usually found in Archean and Proterozoic cratons. For mesothermal deposits, we have a few fun ones. We have greenstone belts, which we've already talked about a bit in the last part, which are an important region for a few of these deposits. They are rich in certain deposit types that are most commonly found within them, although not exclusively. And these belts were formed by ancient ocean basins from layers of volcanic ultramafic rocks and various sediments. Greenstone belts can contain greenstone gold deposits, banded iron formations, or BIFs, and others. Next, we have mesothermal vein deposits, which are similar to epithermal deposits but are formed deeper in the crust. And last, we have pegmatite deposits, which are found in deeply formed granitic igneous rocks and can contain a few rare mineral types. Alright, on to epithermal deposits, which we have the most of. Epithermal deposits are hydrothermal deposits typically found around subduction zones of more recent large volcanoes. Since these deposits are very shallow, they are usually the first to be eroded away. You mainly only find these in more recently formed igneous hydrothermal regions. So then we have Carlin, or sediment-hosted disseminated gold deposits, are rare deposits formed in carbonate rocks. The Carlins themselves formed in an old subduction zone that is now a fault zone in the west coast of North America. Witwatersrand gold deposits, the Wits, formed in the late Archean, so are found in Archean crust, like greenstone belts, but specifically found only on Earth in the Witwatersrand Basin. By a large margin, the Wits are the largest modern source of gold in the world. The next two deposit types form with underwater hot springs, so aka black or white smokers, and will be found in less recent structures, as newer ones will still be in the ocean floor. These are volcanogenic massive sulfide, or VMS, copper zinc deposits, which are volcanic hosted deposits. Sedimentary exhalative, or SEDEX, lead zinc deposits are sediment hosted. They tend to be bigger than VMS deposits but are not as common. Mississippi Valley type MVT deposits are lead zinc hydrothermal deposits that occur where hydrothermal fluids move through limestone, particularly at the edge of sedimentary basins or around any other higher elevation points. Phalore deposits are most likely MVT type deposits that form in carbonate sedimentary rock and can contain a lot of silver. For a fun note, Failure deposits were also a source of stibnite or antimonite, which is a rock that contains antimony. There are other sources of stibnite too, but when powdered stibnite is combined with fat, it creates a black cosmetic that we call coal today. But then the last epithermal deposit is stratiform hydrothermal deposits, which are similar to MVT but in clastic sedimentary rocks, specifically shales. Now let's talk about sedimentary ore deposits, or some of them. Like sedimentary rock in general, these will be at or near the surface in most cases. So first we have alluvial placer deposits, and these contain mainly chemical weathering resistant elements like gold, particularly ones that originate from hydrothermal deposits. And many of the most important placer deposits originated from quaternary sediments, so those from the period spanning the recent glaciation, such as the Pleistocene and the Holocene, and these accumulated along the edges of the ice sheets. Areas of previous glaciation are good sources of rich placer deposits, so areas with high precipitation, like subboreal areas with lots of mountains, can see higher amounts of eroded sediments in rivers and groundwater, forming large numbers of placer deposits. As rivers can frequently change course, you can also find fossil alluvial placer deposits where rivers used to run. The Wits are likely an alluvial placer deposit that weathered epithermal gold veins from greenstone into an ancient island lake. Now, bog iron deposits form in wetlands, namely bogs and swamps, hence the name, by the oxidation of iron carried in the water. They are primarily impure iron deposits, but they are accessible and easy to smelt. The speed of formation heavily depends on the amount of iron in the groundwater. In most places, bog iron takes a few hundred to a few thousand years to form, but areas extremely rich in iron can form bog iron in as little as 20 years. So anywhere with bogs or swamps in the last few thousand years could have bog iron, but areas with current bogs or swamps and groundwater rich in iron will be the most economical. Residual or laterite deposits occur in warm tropical climates, mainly from hydrothermal massive sulfide deposits, as mentioned earlier, where most of the minerals in the rocks have been leached away, leaving the residual minerals. Some laterites are iron-rich, aluminum-rich, nickel-rich, gold-rich, etc., and many types were important sources in early metallurgy. Gaussins are similar to laterites in that they are both weathered or leached deposits that tend to be iron-rich, but these rocks are typically the exposed part of an ore deposit that are found in the oxidation zone, and they experience repeated immersion in acidic water. So immediately below the leached cap of the Gaussin, you typically find an iron hat. Secondary or supergene enrichment deposits are formed from minerals dissolved in groundwater and transported, later precipitating in secondary enrichment zones. These were hugely important in early mining. These are pretty common in all subtropical to tropical, semi-arid to arid environments. These are extremely rare in cold climates where you see a little less liquid precipitation. Evaporite deposits are formed from the minerals left behind by evaporation. They are mainly found in marine basins where the rate of evaporation exceeds the amount of water entering the basin. More recent formations would be in arid and semi-arid regions in closed continental basins. We will also find evaporites that formed much earlier in these areas, particularly where we see retreating shallow seas. Major evaporites are halite, sylvite, gypsum, sulfur, and potassium and magnesium salts. Gypsum and halite, or salt, are commonly found in areas with evaporating salt water like salt springs, salt lakes, and oceans. Marine oolitic deposits form in warmer, shallow water and carbonate sedimentary rock, namely limestone. These deposits were an early, low-grade source of iron. These would most likely be found in either bays or seas on continental shelves near the shore, or in carbonate rock that formed in past shallow seas. Banded iron formations, or BIFs, form in sedimentary rock as layers of iron-rich minerals like hematite, magnetite, and taconite. These were formed when large mountain ranges were eroded and the sediment carried into ancient seas, where they eventually formed chemically precipitated sedimentary rock. An example of this is the Iron Ranges in northern Minnesota. Our BIFs will almost exclusively be found in Archean greenstone belts, but there could be a few created from glacial deposits, which would likely occur along edges of glacial maximums. And fun fact, the hematite from these deposits was a source of red pigment used for cave paintings. Now, a note on mapping ore deposits, which will come up later, is that the distribution of ores and deposits found in modern times is completely misleading for what existed previously. The deposits that were first exploited and most economical in ancient times are either long gone today or no longer economic enough to be relevant. Valuable surface deposits like native copper and silver ores were once abundant but are now very rare. The near-surface deposits that remained past ancient times were those that were considered too low quality to have been exploited before. The prevalence and composition of near-surface deposits cannot be accurately compared to what we find today. We are not going to be mapping all of our ore deposits on one big map or even creating single maps for each individual metal, because realistically this would tell us very little. Hang in there with me. Before we can think about mapping, we must discuss the history, mining, accessibility, and economics of ore deposits. It is not enough to know where different types of minerals are possible, you must also know if they are concentrated enough to be economically viable for a society given their technology level. Throughout history, mining and processing technologies have evolved, allowing people to utilize new resources and take advantage of more deposits than they could previously. Metals in particular were extremely important for civilization as they were used for tools and weapons. When their technology gave them access to a new, stronger, more durable metal, a large technology jump typically occurred. And this is why we typically see historical timelines for different regions split amongst metal ages: the Stone Age, the Copper Age, the Bronze Age, and the Iron Age. I will note that the Copper Age is frequently lumped in with the Bronze Age. The Metal Ages began the earliest around the Middle East. Here, the Copper Age began in the late 5th millennium, the Bronze Age began in the late 4th millennium, while the Iron Age started around 1200 BCE. Now, it is extremely important to note that this sequence of Metal Ages which occurred in the Mediterranean world is not always applicable. For various reasons, such as not having access to all the resources for an age, ages could be skipped or reached at the same time, etc. For example, sub-Saharan Africa started all of these ages, post-Stone Age, at essentially the same time, which was an indigenous innovation, not something they were taught from outsiders. A major source for this section is the book Archaeometallurgy, Material Science Aspects by Andreas Hauptmann. If you're curious, archaeometallurgy is exactly what it sounds like, a type of archaeology that studies the historical human use and production of metals. It is surprisingly difficult to find sources on where and how we got different metals and resources in different stages of history, particularly in ancient history. The deposits we get most of our metals from today are based on which deposits we haven't already used up, which ones are most economical based on our current technology levels, which tends to be higher grade deposits. Some of the most important deposit types today were entirely irrelevant just a few hundred years ago. In order to figure out where important resources per technological age would be located, we must take a good look at ancient metallurgy. When it comes to our assumptions, something important that Nikolai of World Building Pasta explained to me is that there's a tendency for people to think of metal ores in terms of a video game resource, where there are a limited number of significant deposits and all these deposits are essentially equal. In actuality, it is a scale from small, unminable, scarce deposits to industrial-scale productivity. Many deposits will fall in the middle where the value of the resource at the time, and how expensive it is to mine at the time, will determine whether that deposit is worth mining or not economically viable enough. It is all very complicated and can even vary from year to year. So until the Roman period, there were only 9 metals and semi-metals that were known to be distinct ores, and there could be some arguments made for bismuth, nickel, arsenic, and manganese, but these were mostly very localized and or ambiguous. The years we are thought to have first produced these 9 ores are, for copper, since the 8th to 5th millennium BCE, gold since the 5th millennium BCE, lead since the 5th to 3rd millennium BCE, silver since the 4th to 3rd millennium BCE, tin since the 3rd millennium BCE, iron since the 3rd to 2nd millennium BCE, antimony, since the 3rd to 2nd millennium BCE, mercury, since the second half of the 1st millennium BCE, and zinc, since the late Hellenistic period, which is like 100 to 30 BCE. But before we get into metals, we must start with their predecessor, stone. So the Stone Age covers a very large period of human history. The exact years differ, but some say the Stone Age could have began as early as 2.6 million years ago and lasted until around 4000 BCE, depending on the area, when the Copper Age began. The Stone Age is usually broken into 3 periods given its length: the Paleolithic, Mesolithic, and Neolithic. In addition to materials like bone and wood, humans used a variety of rock types to make stone tools based on what was available. The process of carving stone tools, predominantly from flint and obsidian, required an immense amount of skill. There's a very cool video by Hannah Smith called The Lithic Industry and How It Works, where they explain how stone tools were made, and I highly recommend checking it out. It was a really cool watch. So during the Stone Age, most rocks and minerals were gathered from stream placer deposits and weren't mined out of the ground. Chalk flint was the most frequently used and preferable when it was available. If you want to learn more about rocks used in the Stone Age, Prehistoric Technology by D. Semenov in Section 2, Stone Tools, dives into many of the options for stone tools, their prevalence, what properties more or less made them suitable, and it will be linked in the blog post. But from a world-building perspective, there will always be a rock that stone tools could be made out of, and while rocks like flint were ideal, there wasn't an overly huge technological advantage if you had to use a less ideal stone. Unless you are world building for a Stone Age world, you can probably skip mapping the Stone Age, although knowing where flint and obsidian are could be interesting. If you didn't catch it earlier, this is obsidian, which I just think is a ton of fun. But yeah, feel free to skip ahead. But let's discuss where some of the most common rocks to make stone tools out of can be found. First, we have flint, which is a sedimentary rock commonly found in chalk and limestone, which you should recall is a carbonate sedimentary rock, and in sediment alongside riverbeds. There is also a freshwater variety of flint that is found in gypsum, which is a chemical sedimentary rock, around freshwater shores. Obsidian, or volcanic glass, is a felsic igneous rock. Obsidian outcrops are found around volcanic regions, especially rhyolitic igneous provinces. Quartzite, used especially in the older Stone Age, is silicified quartz sandstone, a metamorphic rock. It was mostly only used if there was no flint and is likely to be found in the highest abundance in orogenies, but can be found in most places. There are honestly few areas where it cannot definitively be found. Nephrite, such as jade, is a silicate metamorphic rock that typically formed in subduction zones. Then we have agate, which is pretty common in many depositional environments and is usually formed in igneous rock, especially rhyolitic igneous provinces. Basalt is a magmatic rock found around mountainous volcanic areas such as basaltic provinces. And then liprite is also found in volcanic areas, especially rhyolitic igneous provinces. So now let's map our Stone Age. Okay, so let's start with flint. So to keep things simple, we're going to map these starting with the most to least optimal so we won't have overlapping regions. So first, in your carbonate sedimentary rock and downstream along major riverbeds, we're going to add flint. And then in your rhyolitic igneous provinces, we are going to add obsidian. And then in your metamorphic rock in convergent mountain building regions, we're going to liberally add quartzite. Realistically, this will also be in most places, along with everything else we are yet to map, but locally there may be use of other stones, so just assume everything below quartzite in the key also will have some amounts of quartzite in them as well. So that's basically nephrite, agate, basalt, and liprite would contain quartzite as well. So then in your metamorphic rock in subduction zones in a few places, we're going to add nephrite jade. And then in depositional environments from igneous rocks, particularly rhyolitic provinces, add agate. And realistically, this will gather in our land sediment areas downhill of our mapped obsidian. In your basaltic igneous rock, we'll add basalt. And then in our remaining volcanic areas, we will add liprite. And then everything else that's left, just fill in with quartzite. And this is our Stone Age map. So before we proceed to the next age, we need to talk about fuel. Smelting requires a lot of fuel, probably either wood or coal, so if you don't have a lot of forests or a lot of coal, significant smelting would not be possible. We're going to start a separate fuel sources map where we want to place these 3 resources: peat, coal, and wood. So peat is a sort of proto-coal. It eventually carbonizes into coal, and it can be used as a fuel source that is relatively affordable. As a source of heat, peat is less efficient than wood or coal, and peat is generally found in temperate or boreal forests, where there is high precipitation but lower temperatures. This is namely due to recent glacial activity in those areas that have reshaped the land in a way that is particularly conducive to bogs. Peat also forms in deep but far less accessible deposits in tropical forests, but we won't worry about those for our purposes here. And the greatest areas of peat will be peatlands, bogs, mires, etc. So our global maps are not granular enough for most of our peatlands, bogs, mires, etc., but we can place them in any that we do have mapped in our wetland biomes, as well as marking areas that peat could be found in temperate and boreal forests, particularly those in areas of receding glaciation since the last glacial maximum. So you can sort of see that these are all relatively poleward peat deposits, and they all just sort of overlap with those different forest biomes. So coal is commonly found with shale, sandstone, and limestone in sedimentary deposits. It contains a lot of carbon from plant remains, so it is mostly found where there are prehistoric forests and marshes, and I do mean prehistoric. The time when modern coal formed would be so far back that modern climates would be entirely irrelevant, so it's hard to be specific about where it would have formed. But a decent estimation would be to mark areas on your last supercontinent, which if we consider a similar timeline with Pangaea on Earth, which would have been 300 to 175 million years ago, that would have been in roughly temperate to tropical climate ranges, we'll say 45 degrees north to 45 degrees south. So you can sort of see here me looking at that last supercontinent and marking that 45 degrees north and south lines, and then tracking those shapes to where they move into my new continents and marking which ones were previously in that zone. So within these areas, we're going to place a smaller amount of coal in our non-mountainous carbonate and clastic sedimentary regions. Within these regions, the coal will not always be sufficiently exposed for mining efforts, and a lot of coal is actually mined in mountainous regions, formed by old orogenies because over time that erosion has exposed these older rocks. So within these places, our little, blue areas down here, we're going to place a larger amount of coal in our mountainous regions as patches where sedimentary rock and coal might have been exposed. And these areas won't be sedimentary on the global scale, but could still have exposed coal in them revealed by erosion. Now, if you want to be more specific, you could try to target areas that are more likely to be low-lying, wet, and with rapid sedimentation from nearby mountains, but this is a bit difficult to do unless you have very detailed elevation or topographic maps. But you can see here, we have a little bit of sparse coal out in these sedimentary regions, and then a lot more densely in our mountainous regions. So now wood. Wood is a very common fuel source, especially for household use. Wood is also pretty efficient as a fuel source, but it produces less heat than coal. So wood, however, can be turned into charcoal, which is more efficient than coal, but does take more work to produce the charcoal. Anywhere you have a forested biome will obviously have wood as a resource, and some of the biggest early iron production operations were made possible by over-consuming the available wood resources in an area, which is obviously not sustainable. And it is good to note that deforestation can cause a lot of adverse effects for populated regions, which is just something to be aware of. But go ahead and mark all of your forest biomes as high wood sources and woodlands as moderate wood sources, and then wetlands can be rolled into any of your adjacent zones. There are many other types of fuel, though some aren't as prevalent as heat sources for smelting, and others are a bit too modern to consider here, or just too small scale. So this is what we're going to work with. Let's establish a few quick mapping principles. So mapping deposits on a global scale is tricky because you have to consider how high grade the deposit is, how large the deposit is, and how many of the deposits may be in an area, how accessible they are, etc. We are going to attempt a simplification that will hopefully give us an idea of how rich an area's deposits are, telling us what regions will be major sources of that metal and which resources will only have access to maybe a small amount. To do this, I have gone through the deposits and determined the rough size of those deposits in a given area and how high grade they tend to be. For each metal that we map in this way, we will place the metal by richness. When we overlap, obviously the richer level will win out. We won't get into this level of detail for all metal types because sometimes it just really doesn't matter. The Copper Age, unlocked with the ability to smelt and work copper, is frequently lumped in with the Bronze Age because it was historically a relatively small stepping stone before bronze. Nonetheless, we will be discussing the main minerals and ores of the Copper Age separately. So copper and gold were the most important metals of the Copper Age, followed by silver and lead. Copper was extremely impactful in that it was much harder and more durable of a substance to build tools from than stone was. Copper was also more malleable, meaning it could be formed into far more shapes and complex tools compared to stone, while also being able to hold sharper edges, hold heat due to conductivity, and be resistant to corrosion. But even before the proper metal ages began, people were experimenting with fire and working with metals. Native copper was used for its color, green, and made into beads, ground into powders for cosmetics and paints, etc., before it was even worked into tools. Preliminary copper metallurgy was discovered independently in several regions between 9000 and 4000 BCE and had spread through much of Europe and the Near East by 3000 BCE. Most areas began working with native copper, which is pure enough copper that it didn't need to be melted and extracted from ores. And in this preliminary stage of working with native metals and melting rocks, we also see experimentation of heating other different resources. For example, cement and lime plaster was made by burning limestone, calcite, or gypsum into lime. This was all likely a natural progression from firing clay for pottery. Evidence of using high temperatures and extraction in metallurgy started at around 6,000 to 5,000 BCE, with the first evidence of copper smelting coming from 5400 to 4500 BCE, around the official start of the Copper Age. Due to the abundance of copper at the surface at this time, it is not surprising that evidence of the earliest copper mines only dates back to around 4500 BCE. They weren't needed everywhere at first. Metallurgy at this time was small scale and happened within settlements after transporting the raw materials from their source. This is known as domestic model production, aka production happening domestically. And this was in line with smaller degrees of specialization and less need for mass production and industrial type production of these periods. Areas with particularly rich gold or copper deposits tended to develop metallurgy soonest, and those with the richest deposits seem to have developed more stratified social structures the soonest, along with the mass production of gold and or copper items. But again, this is an extreme simplification, and this is maybe a little bit of a reach, but there's a little bit of patterning there. The huge availability of precious metals would require more stratification and organization to manage large-scale production in general, breaking away from the domestic model. While not a hard and fast rule by any means, there certainly seems to be a correlation between the available gold and copper and the earliest complex societies and states that form. But again, not a hard and fast rule, not conclusive, just a little bit of patterning. Archaeological evidence in the Mediterranean and Near East suggests that copper followed by gold metallurgy came first, with silver and lead coming later. This does not directly correlate with the ease of smelting, so there were clearly preferences for copper and gold, although likely that could have been because copper and gold could have been used natively or cold worked without requiring smelting, and then you get into the earliest smelting at the lower temperatures, and then perhaps into actually smelting copper and gold. But the easiest ores to smelt are tin and lead, which have extremely low melting points, meaning that they can be smelted on a campfire. Tin melts around 232 degrees Celsius or 450 degrees Fahrenheit, and lead around 328 degrees Celsius or 622 degrees Fahrenheit. It is possible that there was an instance of lead smelting predating copper smelting, but the evidence for that is not conclusive or particularly convincing. Copper, silver, and gold have slightly higher melting points. They require higher temperatures than a campfire, so typically small crucibles in this age, and fuel sources like coal that burn hotter than firewood. Copper is a fairly abundant, malleable metal found all around the world and can even be found in a pure state, like I mentioned, that doesn't require much processing, though it is usually found in other minerals such as cuprite, malachite, azurite, bornite, etc., and then smelted to extract the copper ore. In the late Neolithic, there was still relatively abundant ore deposits at the surface, including native copper, which are long gone today. For the Copper Age, we will mostly care about surface and near-surface deposits of particularly native copper. Copper minerals can most commonly found in basaltic igneous and then clastic sedimentary rocks. It is commonly found in deposits with gold, silver, zinc, and lead, and surface and near-surface deposits of copper and gold were very abundant near large metallogenic belts. Alright, so on to mapping the Copper Age. So we do not want to be stingy with mapping our copper. You're going to want to concentrate most of it around your major metallogenic belts, which are your continental convergences that used to be continental oceanic convergences, and then the second most around your subduction zones. And I would recommend going in and marking these areas as copper rich, which is what I did in a light green color, which you'll see on the next slide. But in most regions, the earliest source of copper was going to be native copper, which was used even before smelting was available. And so we're going to map two major sources of native copper, which you can see in this table down here. Failure deposits and secondary enrichment deposits near VMS deposits. And then we will map a few instances of rare native copper in copper-rich areas. And also as a note, the earliest and most commonly used alloy of copper versus native copper was naturally occurring arsenical copper, as it was found abundantly in copper-containing near-surface deposits. I'm not going to show this little cheat sheet on every single page, but you have it if you want to go back to it. Alright, so here I have added all the copper from failure deposits, which is mostly going to be poor richness and rare moderate richness. So you can see, it is hard to see, but you can see a few instances of richer over here, and then most of the rest of these are all poor. And these are going in carbonate sedimentary rock around our basaltic lips. And then here's adding in copper from our secondary enrichment. And this is, again, secondary enrichment from VMS. It is some poor and some moderate zones. And secondary enrichment zones are going to be near our igneous provinces, mainly island arcs and orogenic belts, in all subtropical to tropical, semi-arid to arid environments. And most common in sandstones, specifically, you know, our clastic sedimentary rock, especially alluvial fans. So you'll sort of see those in a couple of my big delta areas there. So now we're adding in a little bit of just extra native copper, and this is going to be rare moderate zones, and just add a few here or there in your copper-rich areas, and you can see those marked out. So then here we are adding our copper from arsenical copper. And this is just small amounts, mostly poor and a bit of rare moderate zones. And these are going to go in copper-rich areas, most likely around coal and clastic sedimentary rock in previous shallow seas. So you can sort of see I filtered those out in there. They're not directly in our copper-rich areas, but they're sort of in those general vicinities. And then here are all the Copper Age copper deposits shown together, and you can definitely see there's certain areas that are a lot richer in copper, areas that are not so rich in copper, etc., which is good. We want that. You want to see that distinction where there's a little bit of clustering going on, right? That'll keep it interesting instead of being entirely uniform, because if it's entirely uniform, why are we doing this? But okay, let's move on to Copper Age gold. Gold is a rare and malleable precious metal, good for forming into jewelry, idols, coins, and many other decorative items. It was valued almost universally across all different cultures and regions, making it a popular trade item as well. And interestingly, until the Bronze Age, it was almost exclusively traded as dust, which is cool. But we are going to be mapping gold from our alluvial placer deposits, laterite deposits, and gosens, as you can see here in this table. So first, the gold from our placer deposits. And these is going to be the most common gold that we're adding, mostly moderate and some rich zones. And there's two things you're kind of looking for here. It's a little bit complicated. You want to look for where the placer deposits are going to form and where you're going to have that gold-rich sediment to form them. So for the placer deposits being most likely, you're going to be looking for areas of previous receding glaciation to be the richest. Also, these would be rich in areas with high precipitation, with lots of mountains. You can see higher amounts of eroded sediments in rivers and groundwater forming large numbers of placer deposits. And then gold-rich sediment is most likely to erode from the areas of rhyolitic andesitic igneous rocks and fold-thrust belts of continental collisions, mostly correlating to our rich metallogenic belts. So you can sort of see where I've added those in. There's a lot up here, a little bit sprinkled in down here, a wee bit there. And then next we're going to add a possible optional ultra-rich placer deposit, which is sort of going to mimic the Wits. And this is going to be very, very rare, rich zone. You'd be looking for an area of uplifted crust below Archean crust, so like greenstone belts. And this is to replicate where there may have once been ancient inland lakes filled with rich gold from greenstone belts that have now been uplifted and eroded to expose those rocks. And this could be an incredibly rare, incredibly rich source of gold like the Wits, although these probably wouldn't have been mined until later, but it's hard to tell based off the area they are. It might have been mined here as well, and you can sort of see I added mine right there for fun. So next we have gold from laterite deposits, and these are going to be some poor regions, and you'll find them in warm tropical climates along greenstone belts. So I mostly have those in through here, a little bit in and around here, and I have one little one right there. So then we have the gold from our Gossan deposits, which are going to be some poor and rare rich deposits. And these are going to be gold-heavy VMS deposits, or where there are gold-heavy VMS deposits, which is going to be in igneous provinces, typically island arcs or orogenic belts. So you can sort of see I have one there, a little bit along here, some in here, one there, a little bit across there. Like they're just kind of sprinkled in. And then altogether, this is our Copper Age gold map. All right, so next is silver. So silver is another rare and malleable precious metal used in the same ways as gold for much of history. The ability to extract silver from lead may not have been discovered until the Bronze Age, though. It's hard to say for sure with metallurgy from this long ago, and the ability to extract silver from silver copper wasn't established until about the 15th century Common Era, but again, it's hard to say with, they're not exact ages and things can be different in a fantasy world or whatnot. But for the Copper Age, we will mainly care about pure silver surface deposits, which were rarer than the other surface deposits we have looked at. And you can sort of see those down here. We have some Gossan, secondary enrichment, and placers of failure sediments, which is going to give us the best chance of that native pure silver. So first we're going to map silver from our Gossans, and these will be some poor and some very rare rich deposits, and these will be alongside where your gold Gossans are, so AK in some igneous provinces, typically island arcs or orogeny belts, and you can just kind of dot those right down next to them. I don't worry about overlapping too much when I'm doing these because they're global maps, they're already incredibly imprecise, so I just kind of try and get them in the right area, and if I ever had to go back and do a more detailed map, I would be more specific about it, but I just don't ever have anything overlap here, so it's fine. And then we're adding some other Gossan deposits that do not overlap with our gold ones, and these will be some poor, rare, rich zones, and these are going to be more in epithermal vein deposits, aka more recently formed igneous hydrothermal regions. So basically that just means your newer active hydrothermal regions, so like subduction zones, maybe your island belts. And now we have silver from secondary enrichment zones. These will be some poor and rare moderate zones. We're looking for secondary enrichment zones near igneous provinces, mainly island arcs and orogenic belts. And this will be in all subtropical to tropical, semi-arid to arid environments. So basically anything that's not humid or colder. And these will be more common in our clastic sedimentary rock, aka our sandstones. Pretty hard to see, but I can tell there's one down here. There's one up there, I think. Yeah, you'll just have to trust that they're there. The silver ones are really hard to see. And then we have silver from our placers, and these are going to be specifically placers that are made from failure deposits, or failure sediments. And these will be rare poor and rare moderate zones, so just rare all around. And these will be downriver of carbonate sedimentary rock around basaltic lips, which is where we would have silver-rich Phalord deposits. And then next we're going to do, oh, no wait, here's our Copper Age silver map. All right, so this is also our final Copper Age map. And so a couple notes with this. Tin and lead were mined this early, but not as relevant. They weren't as relevant until the Bronze Age, so we will cover it there, although those were to an extent mined this early. A lot of the earliest copper and gold extraction, so gold especially, would have been native metals where they can be cold worked and don't require fuel sources at all. So Copper Age metallurgy thus isn't limited to areas with extensive fuel sources, so we're not going to do a comparison of, okay, here's the resources, here's the fuel sources for the Copper Age. But areas with deposits that aren't native metals would have needed some level of smelting to extract the ores and would thus require fuel sources. These areas would need wood for making charcoal or coal. And you can assume that most areas with the copper or gold would have either had enough native metals in the deposits or a sufficient fuel source. But if you want to go through and mark a few that were likely not capable for either region, go ahead. I am not going to worry about it for this example world. Let's talk about the Bronze Age. The importance of the discovery of bronze cannot be understated. Bronze allowed for much harder and more durable tools and weapons than before, giving the first civilizations to unlock this technology a huge advantage. These civilizations were able to dominate and outcompete their neighbors, creating some of the first empires. Likely spurred by economic demands, the Bronze Age comes with a large number of mining and metallurgy innovations. Some of these include the draining of pit mines in more tropical regions, deeper shaft construction, and smelting furnaces. To support this new industry and mass production, smelting in this age transitioned from a domestic model to a market model. Processing happened near the mines instead of in villages, and this all required more labor specialization and social stratification to manage operations, leading to larger and stronger states. Like I mentioned before, this is not a complete 100% correlation there, but it is a little bit of a trend that we tend to see. Bronze is an alloy of copper, meaning it consists primarily of copper along with other elements, and this alloy can be made from melting copper ore with tin or arsenic, or a combination of both, as the primary components, but it can also be found naturally. Smaller amounts of elements like aluminum, nickel, and lead were also sometimes used. Bronze with arsenic is commonly referred to as arsenical bronze, and there are a number of benefits to arsenic in bronze, such as its greater workability, but it is far more dangerous, obviously. Metal workers likely suffered from arsenic poisoning over time, and those that used these tools and weapons would have been exposed as well. It is hard to know how aware Bronze Age societies were of the dangers of arsenic. The dangers may have been a factor for some to prefer tin bronze. Many societies preferred tin bronze also as it was easier to smelt and cast. The availability of different materials would have also had a large impact on which bronze alloy they preferred. In order for a society to unlock the creation of bronze, they needed to have access to copper and smelting technology, as well as access to fuel sources such as coal, lots of wood, and tin and/or arsenic, either separately or naturally occurring with copper. We already have our copper mapped, which is very abundant already, but more deposit types would be available in this age along with the advancement of mining technology. When it comes to making bronze, tins or arsenic are much more likely to be the limiting factor. Surface deposits of copper, particularly near-surface arsenical copper, would have been used in this age as well, but higher-grade mine deposits would also now be utilized. These are still not the type of deposits we use today, as they are mostly used up in many places or just not economical anymore. But in the Bronze Age, deposits were typically around 10 to 15% weight of copper to be considered economical, where in modern times we might consider 0.3% weight to be economical. Naturally occurring deposits of arsenical copper and tin copper ores were relatively common and likely would have been used to make bronze before the manual production of alloys. To a larger extent, these surface deposits we have mapped from the Copper Age will still apply. Some of those deposits may have been minorly depleted, but more on a local scale than something that would be relevant on our global maps. However, some of these surface deposits may be too poor or small and thus not economical enough with more advanced mining technologies. And thus not economical enough without more advanced mining technologies. In areas with larger, richer deposits, we could expect a transition towards these deposits. So let's look at copper in the Bronze Age. The majority of our copper deposits for this age will be in current and previously active subduction zone mountains, mainly in the main arc along with gold. And this will be where we have both basaltic and andesitic magmas in the crust. So VMS deposits were the largest source of copper for much of the Bronze Age, as well as some copper skarns and SEDX deposit mining. Copper porphyry deposits are mostly too low grade for mining this early, but some could have been an early source as they can commonly be mined in pit mines versus more difficult tunneling. And we can optionally add a few deposits of this type to our Bronze Age maps, perhaps more likely in areas where they don't have other more ideal deposit types, but are close enough to those areas to have adopted metallurgy as well. And we can also optionally map out some IOCG deposits. These may have been an early source of copper, although on Earth they were mainly found far from areas of early metallurgy and thus mostly mined since the Industrial Age. Where there are IOCG deposits in decently rich copper-gold areas, more likely to be areas of early metallurgy, we can add these to our Bronze Age maps too if you feel so inclined. Alright, so first we're going to add copper from our VMS deposits. And I've taken the deposits from the Copper Age map and put them on a semi-translucent layer to help the new ones stand out, but let us still see where they are. So that's all these like faint ones in there are all the old deposits. But gold from our VMS deposits, and we will have the most of these compared to other types, is going to be some moderate and some rich zones, and a large amount of these where VMS deposits could have been moved onto continents due to subduction or collision, and variations can be found in most igneous provinces, typically island arcs or orogenic belts. So now we have copper from SEDX deposits, and these are going to be some rich, and some of these in areas with clastic sedimentary rocks, and one of the following tectonic regions, either intercontinental rift valleys, failed rift basins, or passive continental margins, for the most part aka land-ocean transitions that are not plate boundaries. So you can sort of see I mostly have these along some of my shores here, where I have my passive continental margins. And now we have skarn deposits. This is going to be some poor copper, and that's why it's kind of hard to see on this map because they're that really faint color. But you'll have a small amount of these in our carbonate sedimentary rock, aka limestone, adjacent to major subduction zones with non-basaltic volcanic igneous rocks, so andesitic or rhyolitic. Then we'll add some optional deposits, and I just put them both here on one map. But yeah, so some from optional copper porphyry deposits, and these will be rare poor ones. These are most commonly found in major subduction zones, aka our rings of fire, where now extinct volcanoes would have eroded away to expose the deposit, particularly in stratovolcanoes with granite porphyry magma, so our rhyolitic regions that are on our maps. And then gold from optional IOCG deposits, rare moderate ones, and that's this one is an example there and right here. These are going to be in areas with large felsic rhyolitic intrusions nearby to major crustal faults, usually found in our cratons, in which case you have to just imagine that there are some intrusions in those cratons on our maps, but cratons? Cratons, whatever. Croutons, no, I'm just kidding. But yeah, because our maps are really only showing not the intrusions. It's a lot more general. There's stuff on those maps that we can't see because it's a global map, and just, yeah. Great. Okay, so then this is our Bronze Age copper map, which looks pretty good. Like, you can definitely see a lot more serious copper coming in here now that we're in the Bronze Age versus the Copper Age, and you can see a lot of those deposits moving towards a lot of our more mountainous regions, but not exclusively. Now we're going to talk about tin. So tin is frequently used in bronze alloys and provides a good deal of strength. Tin is rare, most commonly found in the ore cassiterite, which usually forms in hydrothermal vents and granitic intrusions, although it has some additional conditions for forming, but we won't get into it. On Earth, we see most tin deposits in the tin belts that can be found in former continental margins, so previously the transition zone between continental and oceanic crust. Elsewhere, we can find a few smaller belts of these deposits, but it is a big thing on Earth that the tin is mostly concentrated into a few specific areas, so we want to replicate that. So map your major tin belts in former continental margins, so previously the transition zone between continental and oceanic crust. And you'll want to think about where you've had plates coming together mainly for this. This will mostly be found in our continental convergence zones where past oceans were closed up. So these are a boundary between two plates, a convergent zone, so is this. This is also an active one, but then I have some in my older non-active plate boundaries as well, just to kind of add a little bit of history there, and those are my less major ones. So now we are going to map a few smaller belts in our past and present orogeny belts. But for doing that, you'll map a few smaller belts in your past and present orogeny belts. So rhyolitic igneous rock, where there would be some exposed granitic intrusions. 99% of tin deposits directly or indirectly come from these felsic rocks. And especially subduction zones where there are hydrothermal vents, and in the back arc of shallow subduction zones, which is less magmatic than steeper subduction, and also continental convergent zones as previously subducted crust is pushed on top of mountains. And note that these tin belts are not what we are going to be accessing in the Bronze Age, at least not necessarily, but we'll get there. So at the surface, people would have most commonly found tin in alluvial placer deposits around these areas. So I just kind of showed my river map on here too, but add traces of tin to be found in downhill alluvial placer deposits from our tin belt areas. And base this on your major river map, but make sure to add some fossil rivers as well that aren't directly where those rivers are. And also, we don't have every single river placed. You can be as detailed with this as you want, but again, these are example maps, so I try and keep them from getting too detailed. And so now we're going to look at our copper deposits that overlap with our tin belts, which means that they could have a chance of having tin-bronze alloys. So mark some of your copper deposits in these tin belts as tin copper, so you can sort of see I have a few of them marked here, a few in there, but it all just depends on how these overlap. So now, arsenic. Arsenic can be used in bronze alloys to make them more workable and castable, and toxic. Arsenic has also been used as an embalming agent, insecticide, fungicide, painting pigment in glass making, and even medicines. It can treat syphilis, but you'll probably get cancer as a result. Arsenic is common in sedimentary and igneous rock, especially around volcanoes and in hydrothermal deposits with higher temperatures, and is found in many ores. It is also frequently obtained as a byproduct of smelting, as copper, silver, gold, and lead ores, among many others, can frequently contain traces of arsenic. Two of the most abundant rocks that contain arsenic are arsenopyrite, which is a sulfur iron arsenic, and arsenic trioxide, or pure arsenic. These are the only relevant sources of arsenic ore before the medieval period, but we are only going to be worrying about mostly naturally occurring arsenical bronze instead of just arsenic in general. So what we're going to do is map some arsenic-rich regions in sedimentary and igneous rock, especially around volcanoes and in hydrothermal deposits with higher temperatures. You can be a little bit more generous here than with our tin belts. So you can sort of see I have all those arsenic-rich regions mapped out. And then, again, just like before, mark some of your copper deposits in these tin belts, in these arsenic belts as arsenical copper. So you can see those are the orange colors in there. All right, so we're going to try and figure out where we would be most likely to find bronze metallurgy. And so what we want to do is look for these areas of potential. So we want to map areas that have the ability to make bronze alloys from either arsenic copper deposits, which is fairly common, tin copper deposits, or areas that have copper deposits and tin deposits. A big thing to note here is that tin and copper does not have to be adjacent. Trade was a thing, and basically the trade of tin towards copper-rich areas could have been a very large driving force of early long-distance trade. So when I was going through and circling these, I circled in pink all of our tin copper, in orange all of our arsenical copper, and then this bluey aqua color for tin and copper. I'm going to be mapping these more towards the copper end than the tin end because it's more likely to trade in that direction for this. But yeah, so I have all those circled just to help me out. And then I overlapped, sorry for the key up here, but I overlapped our fuel sources because we also need to have a fuel source such as coal, charcoal peat, large amounts of firewood. For charcoal, one of those. So I basically went through here and looked at the ones that I had that overlapped with fuel sources, so that I can figure out which ones would have bronze metallurgy potential. And for the tin and copper regions, as long as they have copper in a fuel and could trade for tin, I consider that to be sufficient, as long as it was in a reasonable area. I didn't consider the geography for how easy it would be to trade across certain distances. I just kind of fudged it. But we are left with these Bronze Age metallurgy potential regions, which is cool. It's cool. So let's talk about gold. So technologies to refine gold and goldsmithing both greatly improved in the Bronze Age, which in combination with access to deeper, higher grade deposits gives us access to more gold sources to map in our Bronze Age maps. And you'll start to see gold ingots in the Bronze Age being traded, but it wasn't until around 500 BCE that we have evidence of gold coins, which is roughly during the Iron Age actually. But gold was also found as alloys with silver and sometimes copper. Interestingly, the grading of copper was determined by its color in ancient times. I mean, not that interesting, but I think it's cool. The main deposits we will be adding gold from in the Bronze Age are laterite and Witt-type placers. Epithermal and porphyry deposits can also have large amounts of gold, although they were mostly too low grade for pre-industrial mining. We can optionally add a few of those to be accessible now, but most of them would not have been. So we're going to add our gold from our laterites and our Witts. So gold from our laterite deposits will be mostly moderate in some rich zones, and these will be in our warm tropical climates along greenstone belts. And then our Witts-type placer gold is going to be rare, rich zones, and these would optionally be in a couple of areas of uplifted crust below Archean crust, our greenstone belts. And this is to replicate where they may have once been ancient inland lakes filled with rich gold from greenstone belts, and that have not been uplifted, or that have now been uplifted and eroded to expose those rocks. And this could be incredibly rare, really good source of gold, but you know, these probably or maybe would not have been mined until later, so it's entirely up to you whether or not you want to add them. But you can definitely see some of those areas of gold that I've added in here. So now we're going to talk about our optional deposits. So first is our porphyries and our epithermal. So porphyries are going to be rare, moderate zones, and these would be maybe a couple of spots in your major subduction zones, your Ring of Fire, where there are felsic to intermediate volcanic igneous, aka rhyolitic and andesitic rocks. And then the epithermal ones would be rare, moderate zones in a couple of spots in newer subduction zones and can commonly be found laterally to our porphyry deposits. So they could potentially be nearby. And then this is all of our Bronze Age gold. Now, silver. Silver is another rare and malleable precious metal used in the same ways as gold for much of history. It was usually less valuable than gold, but was more valuable than gold in a few places due to some of the difficulties of mining it. Silver is most commonly found in deposits with other metals such as copper, lead, and zinc, so the silver must first be extracted. And the process to extract silver from silver-copper, liquidation, wasn't established until possibly the 15th century, so for our purposes we will mostly be ignoring those deposits. The beginning to middle Bronze Age likely still used mostly native or pure silver, which we already mapped in the Copper Age. By the late Bronze Age, most silver transitioned to being mined from silver-lead deposits, as we were able to extract silver from lead as early as maybe the 3rd millennium BCE, although the process was very complicated. But before we map this, we're actually going to talk about lead. So lead was typically used for ornamentation, so like small beads, and small tools in this age. Lead is most commonly found in the mineral galena and almost exclusively in hydrothermal deposits. The problem with mining lead is that lead is toxic and high exposure, such as by mining it, is lethal. So for societies that were aware of this, this meant that mining lead and silver lead was typically done by the lowest classes in society, or more commonly, slaves. So first we will map our hydrothermal lead deposits for fun, and then our silver lead deposits. So you can see those types that we're going to be focusing on over here. All right, so add our hydrothermal lead deposits. So these are going to be some rich zones, specifically in older volcanic areas and orogenic belts, newer igneous regions, and at the edges of sedimentary basins near volcanic areas. So you can sort of see I have them in this black, dark gray, black it looks black here kind of color. And then we're going to mark our silver lead deposits, which I mostly just did by having lead and silver right next to each other because that's what I did. And this is going to be especially our MVT-like Phalor deposits, some hydrothermal vein deposits, and SEDEX. So from the MVT, Phalor, and hydrothermal, those are going to be some rich zones in carbonate sedimentary basins near volcanic regions, so hydrothermal areas, and some in clastic sedimentary basins. And then from SEDEX, we'll have some rare moderate zones in areas with clastic sedimentary rocks and one of the following tectonic regions: intercontinental rift valleys, failed rift basins, or passive continental margins. All right, so aluminum, or alum, I should have looked up how to pronounce that. But while having a relatively low melting temperature, aluminum, which is 659 degrees Celsius or 1,218 degrees Fahrenheit, it was almost exclusively found in other ores and was extremely difficult to extract. It was only in the last couple hundred years that aluminum was discovered on Earth. However, alum, or aluminum salts, which could be from a number of minerals such as potassium alum, was used fairly extensively since antiquity as a mordant in dyeing, for tanning, as a flocculant, in medicines, and more. Alum specifically is an evaporite that could be found as volcanic alunite, which is common around volcanoes in fumaroles, or around metal sulfide deposits. And there's also some varieties around deserts. So I just added some sprinkles of that around. And then here is our final Bronze Age map. On to the Iron Age. So the Bronze Age was quite long, and that's partially because it took longer than you'd expect for iron to replace bronze. The Iron Age is said to have started around 1200 BCE, but by that time ironworking had already been around for a few thousand years. Bronze is harder and more durable than pure iron, but bronze requires tin or arsenic. Arsenic is toxic, and tin is not very abundant, which greatly limited the amount of bronze that could be made. Iron ore, on the other hand, is very abundant. But the first iron tools and weapons were nothing like we see with steel, as iron by itself is surprisingly a spongy metal, especially bog iron. It was far easier and cheaper to produce large amounts of iron weapons to quickly arm a military force, even though they were worse quality than bronze weapons at first. Iron is one of the most abundant metals on Earth. It's around 5% of the crust. But the biggest problem with producing iron is that it has a very high melting point, melting at around 1538 Celsius or 2800 Fahrenheit. So advancements in smelting were required to work it. Along with the start of the true Iron Age, we also start to see the discovery of steel, an iron-carbon alloy which was perhaps initially discovered by 1800 BCE, but wasn't being produced consistently and reliably until maybe 500 BCE. Claims for that exact year that steel was discovered are all over the place. But steel is much harder and more durable than bronze and only requires carbon to make, in addition to the very abundant iron. Since it took time to find the right amounts of carbon to keep the steel from being too brittle, and time for other discoveries like hardening and tempering to further improve the steel that could be made. Okay, so let's map our Iron Age. So for mapping iron, we have two main sources that we're going to talk about: bog iron and then our pre-industrial iron sources, which you can sort of see those lined out down here a little bit. But bog iron was essentially maybe one of the earliest utilized sources of iron. It would be found beneath current and previous wetlands with iron-rich groundwater. They are generally pretty small, so they would not support a large population, and this resource would be very regional. But pre-industrial iron sources were mainly skarns, sedimentary ironstones from laterite deposits, marine oolitic deposits, mainly falling out of use in favor of higher grade deposits in post-industrial times. Production was typically limited by fuel as much as ore availability. So let's get started. So first, and I'm mapping iron in reds here because I did. So map bog iron as your poor iron regions and thus small-scale Iron Age potential beneath your current and previous wetlands downhill of metallogenic belts, so subduction or convergent mountains. And the largest or most numerous of these will be in your current bogs and swamps with incredibly rich iron groundwater. So look at the mountains around them, whatever would be upriver of them, and the headwaters, if you will, right, and figure out how iron rich would have been being fed into that basin. So you can see I've added those a good bit around here, And again, bog iron is going to be very small, so what we're circling is really just regions that would be more likely to have it, something to give us a little bit of an idea of where we'd be more likely to find this. So this tells us small scale Iron Age potential. So anywhere with bog iron would be an adequate fuel source as well for small scale Iron Age potential, so I sort of just am showing you here an idea of what that would look like. So cutting back in over here, so iron from skarn deposits. These are going to be some moderate and mostly rich deposits. So these are going to be in carbonate sedimentary rock, i.e. limestone, adjacent to major subduction zones with non-basaltic volcanic igneous rock, so our andesitic and our rhyolitic. And the next we're going to add iron from our laterites. And this will be mostly moderate and some rare rich regions, and these are going to be mainly in warm tropical regions near or in large igneous provinces, our lips. So you can see I've added those in here, they're pretty obvious. And then we have our marine oolitic deposits, and I've shown these as pretty big and kind of all over the place, which may have been a choice, but it felt like the thing to do, so I did it. I don't know if that's the exact percentage here, but these are all going to be moderate deposits, roughly, and these are going to be in your marine depositional environments, such as bays and seas on continental shelves near the shore, and in sedimentary basins, so especially in closed continental basins in past shallow seas. Now, I don't actually have a lot of those kind of areas on my maps. Those would be more small scale, kind of within the mountain ranges and regions that I kind of tried to put those in, but I did what I could. And then we have hydrothermal deposits, and this is going to be iron from optional hydrothermal deposit iron sources. So some rich deposits optionally in small amounts in metallogenic mountain belts. So you can sort of see I just added some in there. And then we have iron from meteorites. So meteoritic iron is another source of iron that can be found almost anywhere. You can optionally add this if you want and do it sparingly if you do. If desired, and these were going to be very rare rich deposits. They're a lot easier to find and more likely to have been used if they fall in deserts and icy areas, so try to put them there if you place them. So then this is our Iron Age iron map. So now let's talk about our large-scale potential for Iron Age. We don't have to do anything as crazy complicated as the Bronze Age, because carbon can be found anywhere, for the most part. That's not really going to be a big limiting source, but fuel will be a limiting source here. So charcoal was probably the dominant fuel for most of the Iron Age, although coal would become prevalent later on. So you can mark areas with both pre-industrial iron sources and abundant wood for making charcoal, or some areas that have coal, so maybe all the areas that could make charcoal and like a few of the areas that could make coal as having large-scale Iron Age potential. So you can sort of see I added those in here. With the dark purple color, and I also showed here some of the lighter colors too, back from our bog iron. Alright, let's talk about zinc and lead. So zinc was used medicinally and to create brass, and zinc can also be added in small amounts in bronze alloys to improve the ductility and strength. Zinc is most commonly found in sphalerite, where they had the technology to deal with the containment of zinc gases, which was mainly in India, potentially a few other places. Otherwise, it was mostly found in carbonates. So zinc and lead were almost always found together, other than some VMS deposits that could be lead poor. But we're mainly going to be looking at SEDEX deposits, MVT deposits, and VMS deposits, which would be our good sources of zinc and lead. Deposits with zinc are commonly found in contact areas with mafic rocks and carbonate sedimentary rocks, like limestone. I found this interesting map here of just MVT and clastic-dominated sediment lead-zinc deposits, just to kind of give you an idea of some of these. You have your Mississippi Valley type and your clastic rock ones, and I don't know, it's just cool to kind of see the distribution and how many they have placed there, for an example. But okay, so adding zinc and lead from our VMS deposits. So where VMS deposits could have been moved onto continents due to subduction or collision, aka our older subduction zones with igneous rocks, we're going to be looking at mapping. Variations can be found in most igneous provinces, typically island arcs or orogenic belts. And then from SEDEX deposits, these are going to go in some of the areas in which clastic sedimentary rocks and one of the following tectonic regions overlap. So we've said this list a lot, but intercontinental Rift Valley, failed rift basins, or passive continental margins, aka land-ocean transitions that are not plate boundaries. So then from your MVT deposits, we can add some in sedimentary basins, especially in closed continental basins, and at the edges or higher elevation points of carbonate limestone sedimentary basins. So those kind of areas. So you can sort of see where I've gone through and added those in here in the blue color. So now let's talk about brass. So brass is another copper-based alloy of zinc and copper specifically. It can have a mix of other trace elements as well, just like bronze. And it was commonly used in currency, musical instruments, and various decorative items like statues. And compared to bronze, brass is more malleable and has a lower melting point, but it is not as strong or durable. It is also not quite as resistant to corrosion. It wasn't truly utilized in most places until much later due to the difficulty to make it, as zinc evaporates before it reaches smelting temperatures, which requires the containment of zinc gas, which may have likely been done in India as early as 1000 BCE. Smithsonite ore was perhaps the best common source of zinc used at first for making brass. Zinc was not discovered as a separate element until much later than the discovery of brass. So we can map brass-capable areas, and keeping in mind that not all of these would have actually utilized or had the right exact technologies to do this, it's just possible areas. But you'll want to place these in copper-rich areas that overlap with areas containing zinc deposits. Though we specifically want smithsonite ore or other sources of early zinc, so we'll be looking mainly at carbonate sedimentary rock that has a lot of zinc ore. So you can sort of see I've added that in a few areas here. It's a little hard to see. They're in there. So let's talk about gold. So gold continues to be important in this age. By the start of the Common Era, 0 CE, gold coins were more widely circulated. The gold maps from the Copper Age are going to carry over into this age well enough. We'll just work with that. And around the European Middle Ages, arsenic, cobalt, and nickel were discovered as individual ores. We won't be mapping them though. So this is our final Iron Age map. So something fun to look at is the different capabilities from across the ages. Again, not all these areas would likely develop these types of different metal ages. There's a lot of complications in here and a lot more things that come into play when it comes to people and society and history and conflict and all of that kind of stuff. This just is a fun little look. But you can see there's a lot of areas that have all of them, and where they overlapped I showed, Iron Age on top of the other ages. But you can see there's a lot of more isolated areas that perhaps wouldn't have advanced past, the Copper Age until they start having that traded in. Whereas there's a lot of areas that have a bit of a smorgasbord, and they just have all of it everywhere. So it kind of just gives you some ideas about some ways that, you might see trade developing, ways you might see conflict developing, the migration of peoples, the, attainment of new land, colonialism, all those types of things. Just, it gives you little bits of ideas, and it's a fun map to look at. All right, let's briefly talk about what comes after the Iron Age. The Industrial Age began with the Industrial Revolution around 1760, at least in Great Britain. And this revolution came with many advancements, mass production of goods, and population booms that also required an agricultural revolution. At this point, most of the easily accessible metal deposits were used up or no longer economical, requiring innovations in mining to reach deeper in the ground and more efficiently smelt ores. Drilling and blasting, among other mining innovations, assisted these efforts. The deposits that were considered economical in this age were much lower grade than what was utilized before. There was also a huge increase in the demand for fuel sources, especially coal in this time. Charcoal was still somewhat used, but coal was by far more dominant. I am mostly not talking about this age much, but there were plenty of deposit types that didn't become prevalent until this age, and with deeper mining, more deposits could be reached. A number of resources were also discovered or became prevalent in this age that we won't be discussing. If you wanted to create an Iron Age map, a good place to start would be taking your Bronze Age map, but removing most of the lower grade deposits, and then adding these additional ones. For gold, we have greenstone belts, which are major sources of gold, and Carlin-type deposits are fairly small sources, but they mainly contain microscopic flecks of gold that require pretty modern technologies to extract. For copper, porphyry deposits are low-grade sources of copper but become economical with Industrial Age mining. For iron, bog iron will have mainly fallen out of favor and then replaced for a while with IOCGs as a major source until around 1950, and at this point, way more modern than we are concerned with, banded iron formations, or BIFs, took over as the major source of iron. Let's discuss a few building materials. We won't map this, but if you're curious, the majority of ancient and Middle-aged stone buildings were made of limestone, sandstone, granite, or marble, which I think I have, let's see. I have limestone here, sandstone, granite, and marble. The prevalence of these rocks is largely already mapped out for us, but limestone is our main chemical sedimentary rock, sandstone is our main clastic sedimentary rock, granite is our granitic igneous rock, and marble is a metamorphic rock found at convergent boundaries around where limestone is present. It's a calcsilicate rock. And then bricks are made from clay, which is a type of sediment mainly going to be found in depositional areas like riverbeds, lake beds, and floodplains. So now let's have a bit of fun and discuss gemstones. Gemstones are minerals that can be found on in a number of different regions depending on the conditions and minerals present. Some gemstones, like diamonds, require an immense amount of heat and pressure, only forming deep in the earth, and have to be brought to or near the surface for us to find them. Other gemstones form in hydrothermal deposits where they crystallize in cooling water, like emerald, topaz, aquamarine, and tourmaline. Other gemstones form from metamorphic processes, like rubies, sapphires, and lapis lazuli. And some gemstones form from sediments deposited by water into cracks and pockets, like opal. The origins and exact formations of all gemstones is not completely understood and is debated in many cases, so keep that in mind going forward. If there's a particular mineral or gemstone you are interested in, consider doing additional research. The rarity of gemstone quality minerals depends on the color, quality, and other properties, but we will generally consider rarity based on the most common version. You can assume less common colors like red diamonds, sunset-colored sapphires, icy blue tourmalines are much rarer than their standard gemstone. It's hard to completely compare the rarities of gemstones, but here's a rough idea of the rarity of more well-known gemstones. So, extremely rare will be muscovite, followed by alexandrite. Very rare is emeralds, are corundums, the rarest being rubies, followed by sapphires, and then white diamonds, opal, turquoise, and smithsonite. For rare ones, we have jadeite, tanzanite, spinel, feldspar, zircon, and rhodochrosite. For uncommon ones, we have nephrite, jade, lapis lazuli, malachite, azurite. And then for common ones, we have garnets, zircon, aquamarine, tourmaline, agates, topaz, peridot, and bornites. And then widespread is just others, with quartz being the most common. And another warning, I'm really bad at pronouncing the names of these, even if I know how to pronounce it. I don't know why, but bear that in mind. And now also just be aware that the rarity doesn't necessarily distinguish how many places the gem will be found, but how many gems will be found overall. So for mapping gemstones, we aren't going to map each one. Putting all of these on a single map would be entirely unreadable for my showing it to you. As it is, the map we are going to create is already a little tricky, but the best way to map gems would be one gem at a time on its own map. I will give you the mapping instructions for each gem, a bit more details in the blog post for the ones we aren't doing directly here, but we are only going to create a single map with the rarest, most valuable gems on it. Alright, so now we're going to continue with gemstones and we're going to map them out. My graphics are a little bit weird and all over the place, so I apologize. I just kind of found what I could find or threw stuff in here where I felt like it. But we're going to start by talking about metamorphic rock gemstones. And so this information here is going to predominantly come from the GIA Gems in Geology magazine column, Gems Formed in Metamorphic Rocks by Aaron C. Polk and James E. Shigley. Metamorphic rocks are formed by different temperatures and amounts of pressure, as we've talked about. And so we can consider the conditions for different gemstones that can be more commonly found in them. And you can see that list here on the screen, going through blue schist, green schist, eclogite, amphibolite, and granulite, and just kind of talking about where those would sort of be found and Some gemstones you might be more likely to find in them. But the type of materials present also matters, not just the type of metamorphosis. Is that a word? Metamorphosis? I guess would be correct here. It just seems wrong because we're talking about rocks, not butterflies. But anyway, so what we are going to do is we're going to place mineral sources for these metamorphic gemstones, jade, tanzanite, tsavorite, and lapis lazuli, and then a few that are both metamorphic and igneous we'll do after the igneous section. But so first we're going to talk about jade. So jade has two different main types. There is jadeite, which is rare, and nephrite jade, which is rare but less rare than jadeite, which are both found in metamorphic rock in slightly different areas. Again, they're different rocks, or different gems. Jadeite, which is rare, forms in subduction zones that have basaltic igneous rocks, and it can be found in cratons. Nephrite jade forms in hydrothermal areas with silica present, so we'd be looking for the presence of rhyolitic rocks, which have the most silica, followed by our granitic igneous rocks. And I have a tiny little lemon jade, which I am pretty positive this is nephrite jade, or nephrite lemon jade, not lemon jadeite, because otherwise it would be very, very valuable, and it's not. So next we're going to talk about tanzanite and tsavorite. So these are both gems of the mineral zosite, and they are found in only one area on Earth. They are found in orogenes and calc-silicate rocks, so look for convergent boundaries where limestone is present, aka our chemical sedimentary rock. And then next we have lapis lazuli, and this is found in limestone, so our chemical sedimentary rock. And let's see, I do have a little poor quality lapis lazuli here. They're very pretty. The ones I have are, you could argue that they're gemstone quality, but they're, it's fine. It's for the vibes. But garnet, rubies, sapphires, and quartz can be metamorphic and magmatic rock gemstones, and they'll be mapped in the next part. So let's talk about magmatic rock gemstones, which are found in and around igneous rocks. So this information here is going to predominantly come from a GIA, Gems in Geology magazine column called Gems Formed in Magmatic Rocks by Aaron C. Polk and James E. Shigley. I think you're picking up the trend here. But as magma cools, minerals crystallize, sometimes into gemstones. Many gemstone-bearing mineral deposits that form in magmatic rocks also form in metamorphic rocks. So we're going to start by talking about kimberlites, which we've mentioned. But kimberlites are an igneous rock that forms from cooling magma, typically in vertical shafts that have been pushed to the surface by volcanic eruptions. They are They are almost exclusively found in cratons, aka our greenstone belts. And this rock can contain minerals from deep in the earth, such as diamond and zircon, and can also collect minerals on their way up to the surface. So garnet, kyanite, and spinel are examples of ones. And you can see here, this is the kimberlite structure there, which is cool. All right, so in our felsic and intermediate igneous rocks, so rhyolitic and andesitic, we will also find pegmatites. And pegmatites are granitic igneous rocks, so extrusive versions of rhyolitic rocks, and they are a good source of gemstones like tourmaline, aquamarine, emeralds, topaz, and ruby. There's another type of rock, alexandrites, which are very, very rare, and they are actually typically found in emerald mines. So also in these areas we'll find feldspar. And this is going to be common as a mineral, but very rare as a gemstone, and there's a lot of very interesting ways that they can look. This picture here is of spectrolite, which is very cool and very pretty, but there's ones that look very different to this. And I have a very, very tiny, poor quality amazonite, which has some feldspar in it as well. You can see a little bit of that color in there. It's very low quality, but it's fun. So then, in our mafic and ultramafic igneous rocks, so basaltic and comatite in cratons and greenstone belts, we can find a number of rocks starting with peridot and spinel. Spinel? I don't know. But peridot or olivine is going to especially be found in our greenstone belts, as this is, olivine is mainly what's in those, or it's at least very common in there. And you can just see some cool pictures of these here. And then let's talk about rubies, sapphires, and zircon. So rubies and sapphires are both gems of the mineral corundum. Ruby is rarer than sapphire, and typically ones that are sufficiently red are considered rubies and everything else is sapphires, whether or not they're blue. My engagement ring actually has a pink sapphire on it. Fun fact. But these form from metamorphic conditions in extreme orogeny events in basaltic rock and kimberlites, and some mafic igneous deposits, in addition to pegmatites. So ruby and sapphire can be found near each other, but not always, and zircon is also frequently found with various corundums. So rubies, specifically, may be more common in calc-silicate rocks, so convergent boundaries where limestone is present, aka chemical sedimentary rock, whereas sapphire deposits may be more common in aluminum-rich areas, so typically more tropical areas. And with the pictures you can see here, I just wanted to show just how many colors some of these gems can come in. For example, zircon is typically thought of as a light blue color, but it can be found in all colors of the rainbow. And all those gems right there come from Vietnam. So in a very small area, you can have a large variety in the amount of gemstones from a single type of like mineral that are found. It applies to most of these. I found a cool picture here and we went with it. So then topaz is found in basaltic rocks where fluorine and hydroxyl is present. So you can kind of pick a few distinct locations where this would have been present on your map. We don't need to get overly specific there. And then quartz. So quartz is also extremely common and formed from metamorphosed sandstone in mountain building regions. And we've already mapped this a little bit in the Stone Age. It's basically almost everywhere. It's not worth mapping here, but there are plenty of rare quartz types depending on their color, which we'll mostly just discuss amethyst, but there's also citrine, rose quartz, a bunch of other examples, and I have a giant amethyst, which I saw that picture and it kind of just looks like a nicer version of this, but like, look at this bad boy. Ain't she pretty? She's not super, like you can see, she's not super uniformly purple. It's not as like densely colored and uniformly colored as that one, but it's still really cool. I believe, and I did a little bit of research on this, but just to kind of give a little bit of an idea about the way trace elements can sort of impact different gemstones, amethyst, which also my earrings, and also, I think I have another one somewhere. Let me see. This is also amethyst. And amethyst is purple due to trace amounts of iron and I believe natural radiation and heat. And then I also have, if I can find it, a rutilated quartz, which you can see here. And these have little needle-like intrusions of rutil, which is very cool. Let's see, I have rose quartz, which is lighter with trace amounts of iron, titanium, or manganese. I'm sure you've all seen rose quartz before. I've found it naturally. And then I have some strawberry quartz, which is a little bit darker than rose quartz. And this is has iron intrusions that create the color. And then last, I have smoky quartz, which is cool. It's pretty clear. And this is like a brownish gray color caused by trace amounts of aluminum and gamma irradiation, which is neat. All right, so garnet. So garnet, the origins of all types of these aren't entirely known, but they are found in ultramafic rocks with peridotites in our kimberlites, or in magmatic intrusions in limestone or calc-silicate rocks, or in erupted rhyolitic rocks. And then tourmaline is found in pegmatites and around IOCG deposits in Archean cratons. And I just saw this picture of watermelon tourmaline, which is really cool, and I want one. I hope they're not expensive. All right, so sedimentary rock gemstones. And this information predominantly comes from a GIA Gems in Geology magazine article called Gems Formed in Sedimentary Rocks by James E. Shigley, Rory Basco, and Aaron C. Polk. So we got an extra author in there, you know, keeping it interesting. But gemstones that form in mostly clastic sedimentary rocks include amber, agate, chalcedony, opal, malachite, rhodochrosite, smithsonite, and turquoise. I think I pronounced that. I used to have this problem where I would pronounce it turquoise. I don't know why, but my brain insisted there was a T there. I don't know what to tell you. But note that these minerals did not form as a direct result of sedimentation, but other forces, and a number of other gemstones that were formed elsewhere but ended up in sedimentary placer deposits can also be found here. So these tend to be primarily harder, erosion-resistant minerals. But anyway, turquoise is one of the gems that form in clastic sedimentary rock, and it can be found near copper deposits in typically dry, relatively barren areas. I don't know if that's just where it's more likely to be found, but that's the trend here. And I have a little turquoise, which is kind of boring, not very patterned, but, you know, it technically counts. So then we have agates, which is a type of chalcedony, which is found near basaltic igneous rocks. And we did already map those a little bit, but let's see. Yeah, but we already mapped those before, but I have a little moss agate, which, I don't know how well you can see this. It's like this like green smoky kind of color. It's not as pretty as this, obviously. I have a couple like this, but I didn't want to bust out my entire rock collection. I really considered just being like, and here's the rocks, but they're mostly like not gemstone rocks, they're like rocks. And if you all want me to do like a rock collection walkthrough one day, I can, but today's not the day. So now we're going to talk about malachite and azurite, which are both found near hydrothermal areas or mountains with copper deposits. I don't have either of these, at least not in the tiny little collection I have here, which is mostly my small, not great ones. So then we have bornite, which is found near hydrothermal areas, mainly in mountains. Pretty sure I have some bornite somewhere, but... And then we have rhodochrosite, which is found near ore deposits. And opals and smithsonite, which are most common in ancient seabeds. And opals are actually like pretty rare, which is fun. But then now we're going to talk about placer deposits. And so with placer deposits, you're going to see a limited set of gemstones. You can see a little bit of other ones, but you're going to mainly see a limited set. Are basically ones that can withstand the weathering that requires them making it into these placer deposits, right? So you can place gemstone minerals that may have ended up in placer deposits around the original sources, mainly further down in the like drainage basins in your river watersheds. We mapped that in the rivers part, you know what I'm talking about. But that list is here, so you mainly see agates, aquamarines, another beryl like morganite, alexandrite, ruby, sapphire, and other corundum, diamond, emerald, peridot, quartz, amethyst, agates, especially around sandstone and shale, and granite and other felsic igneous rocks, spinel, topaz, tourmaline, and zircon. And here's just like a cool graphic here showing like how placer deposits end up and how the rocks tend to get sorted based off, you know, their size and weight and all that. It's fun. But we are going to be mapping just the valuable gem maps. And as I said before, this example map is going to be very limited. Feel free to create separate maps for all the gem types that we've already gone through. There'll be slightly more description in the blog post, but there's not a lot of overly specific stuff about these. Like, it's a little tricky, but feel free to do that, or feel free to create more regional maps just with areas of interest where you can kind of get more gems on them. But for our reference, we're going to start by placing our kimberlite and pegmatite gem-bearing regions or districts. So we're going to place kimberlite areas in our cratons, aka our greenstone belts, and you won't find these kimberlites in every craton, but maybe select some cratons to be particularly full of kimberlites, others to only have one or two, and some to have none. And your shield regions will tend to be a little bit more bare just by my looking at maps on this. And you can sort of see those are these like yellowy dots. They're a little hard to see, but they're there. And then place your pegmatite areas, which I have in this like light lavender color, in felsic and intermediate igneous rocks, so rhyolitic and andesitic. And while pegmatites are fairly common, those bearing gemstones are pretty rare. So you might have a couple areas with some clustered pegmatites, but they will tend to be spread out. And they will be more likely to be accessible in older and past orogenies. So Now we're going to go through and map our rarest and most valuable gem types, or whatever list of gems that you'd like. So I made a little table here of the ones we're going to map, mostly just the most rare ones. So emeralds and alexandrite gems. So emerald gems are very rare and will be mostly found in pegmatites in a few regions. We've already gone over most of this, but follow along. So alexandrite gems are extremely rare, and these should only be in a few of the places you'd find emerald. So you can sort of see here, I have some over here, I have some here and here, right here. That's all I can make out from this far away. And then adding in ruby and sapphire, so these are very rare, with sapphires being the more common of the two. And these are most likely to be found in our partially eroded mountains and basaltic rock and kimberlites and some mafic igneous deposits in addition to pegmatites. Ruby and sapphire can be found near each other, but not always. Rubies may be more common in calc-silicate rocks, so convergent boundaries where limestone is present, aka chemical sedimentary rock. And you can see I have like clusters up here, a little bit over here, some here, down here, here, and along in here. And then sapphire deposits may be more common in aluminum-rich areas, so more tropical ones. And I don't actually have a lot of more tropical landmass, so I didn't actually end up with that many, but where I have these areas, I tried to put a lot. So those are here and here. And something to note, and there's a reason why you want to note the rarity, is that even if maybe there's a ton of gems, if it's a really rare one, the odds of you finding one in those areas are still pretty low. So even if you have a dot, one dot is not the same as another dot. Yep. So diamonds are very rare and are found in a small number of kimberlites, but most of the ones that we've mapped here would be capable of having diamonds, so they can go in probably a good number of your mapped kimberlites, because there'd be a lot more than we mapped. So you can sort of see, these are especially hard to see, but I have a good number here, here, basically anywhere I have these big clusters, I tried to have them in there, and then I sprinkled them in some of the more isolated ones as well. So then opals and smithsonite are very rare and will both be found in clastic sedimentary rock that used to be ancient seabeds. So we look at our shallow seas maps. And there will be 1 to 2 major regions for each of these. So for opals, which are the lighter blue color, which I think right down here I have some, and I have some right in here. I think I might have like 1 dot there, but those are the main areas. And then for smithsonite, I have up here, down over here, 1 there, a couple here. I think those are the main areas I have those. So then turquoise is very rare and will most likely be found in clastic sedimentary rock, mainly near copper deposits in dry, relatively barren areas. So you can sort of see, like I have those right there. I think some of those might be turquoise, that might be turquoise there too. So then tanzanite and tsavorite are rare and go in orogenies and calc-silicate rock. So we've already, aka convergent boundaries where carbonate sedimentary rock, aka limestone, is present. And these will probably only be in a single region or two, so I just have this listed here as tanzanite. And there's a little bit over here. I think I have some down here and up here maybe. And then spinel is rare and can go in some kimberlites and some basaltic regions or cratons. So those are really easy to see, right? More common than the other ones. And then here are all the main deposits for our rarest and most valuable gems. But gems are commonly found in placers, not just necessarily mined from their original host rock. So for reference, we will map the main areas of our placer deposits. Alluvial placers are going to be our main source of gemstone, but feel free to add a small number of other types of placers if you so desire, so you can reference the depositional environment section from the last part. But mark your alluvial placer deposits, and these placer deposits will mostly fall in our land sediment regions, but can be fairly small and not big enough to register on our global map. So just keep that in mind. But these will mainly be found in alluvial floodplains, river deltas, along major river bends, etc. And these will be areas of, or most likely in areas of previous glaciation, of rich placer deposits, areas with high precipitation like subboreal areas with lots of mountains. In these areas you can see higher amounts of eroded sediment in rivers and groundwater forming larger numbers of placer deposits. And then as rivers can frequently change course, you can also find fossil alluvial placer deposits where rivers used to run. So you can place these regions in a general vicinity of rivers. So you can sort of see, I just kind of roughly added some placer deposits there. There would be a ton of smaller ones, but again, this is a global map, so I kind of just tried to give a general idea of what could be there. And then from our original deposits, these are the placers I ended up with. And you can sort of see that they're definitely clustered, more so in some of my more major river basins. And then the ones where I just have kind of lone rivers, they tend to be a little bit more spread out there. And then showing all of our deposits, gem deposits together, it looks like this, which is pretty cool. Like, you can tell just from the colors that are definitely regions that would be more gem heavy, regions that would only have maybe 1 or 2 different types of gems. And again, if I was really world building this out and I wanted to know for a certain region, I'd probably go through all the gem types and figure out what would fit there. But this does a pretty good job for what we're talking about today, and I think gives you an idea of how you can map these. And honestly, most of the goal here is that I've given you enough of a foundation, enough groundwork to have already been completed that if there's something specific you want, you can do a little bit of research and then you already have the entire foundation to be able to figure out where it goes. So like if there's a gem we haven't placed here, do some research, figure out where it's from, or even look at maps of it and cross-reference the maps of where those gems are found with some of the rock distribution maps of Earth, and then figure out where those might be here. Like, you can find whatever you want. Hopefully with what we have here, at least is a good starting point. But yes, that's gems. Now that we have our metal ages mapped, we can go in a few directions. We can create our regional maps, which I plan to eventually create a guide for, and we can start by adding people. I have started my society and cultural world building guide already, which I will link below, and already out are the videos on cultural divides and physiographic regions, migration, extinction events, and available animals, domesticated animals and beasts of burden, and mapping early civilizations and states of antiquity. The next part in this series, hopefully coming out in the next month or 2, is Middle Age maps and colonialism. I haven't decided what will be next, but possibly the Age of Discovery and International Trade. If you'd enjoyed this video, please like, comment, and subscribe, and I have a Ko-fi if you want to support the channel. I also run a world building Discord that is semi-private, but if you're really into world building, fill out a request on the Contact Me form on my website and I can send you an invite link. There's also a private section in that Discord that you can only access by being a Ko-fi member at a certain level. But thank you so much for watching. I've had a ton of fun making this video, and I will see you in the next one.